Hello everyone, welcome back to my VLSI diary. My name is Shivangi Upadhyay and in today's video we are going to explore the basic concepts of digital electronics, the true foundation of every VLSI design. Before we start writing Verilog or diving into RTL design, it's really important to understand how digital circuits think, from logic gates and combinational circuit to sequential elements, FSMs, memories, and buffers like FIFO and LIFO. By the end of this session, you will clearly see how all the building blocks come together to form the logic inside every chip. So, let's get started and bring digital concepts to life one gate at a time. So, digital electronics is the branch of electronics that deals with the signals having discrete values, usually 0 and 1. Unlike analog systems where voltages vary continuously, in digital circuits, we use logical states, either on or off, to represent and process information. Now, in context of VLSI design, digital electronics plays a foundational role. Like it enables deterministic and scalable circuit behavior, which means every input patterns always produces a predictable output. This makes simulation and verification possible even for chips with a billions of transistors. Modern chips are built using RTL-based design flows described in Verilog and System Verilog, where logic is automatically synthesized into gates by EDA tools. This automation allows designers to focus on the behavior while tools handle the optimization for performance, power, and area. Digital design also promotes modularity and IP reuse, like blocks like ALUs, memory controllers, and UARTs can be integrated easily into a larger systems. Another advantage is noise immunity. Since digital circuits recognize only two levels, small voltage fluctuation does not affect the logic operation. And though ADCs and DACs, digital systems seamlessly interact with the real analog world. For example, in sensors, communication systems, and signal processing. So, in short, digital electronics gives VLSI designers a reliable, automated, and scalable foundation to build the complex chips that powers today's technology, from microcontrollers to SoCs and AI processors. Now we review the logic gates. These are the basic building block of any digital circuits. They perform logical operations on binary input 0 and 1 to produce a single binary output. Every complex digital circuit like processors and memory is made up of combination of these simple gates. Let's quickly go through the main types of logic gates. Number one, AND gate, which gives 1 only when all inputs are 1. Second, OR gate, which gives 1 when any input is 1. Third is NOT gate, which simply inverts the input. NAND and NOR gates are also called universal gates because we can build any digital circuit using NAND or NOR gate. XOR gate gives output 1 only when inputs are different, and XNOR gate gives output 1 when inputs are same. Logic gates act like the decision makers of digital systems, turning simple 0 and 1 into meaningful logic and computation to make bigger systems think and decide. So, in summary, logic gates are like the neuron of the digital electronics. They take binary signals, apply logical decisions, and together form the brain of every VLSI system from microcontrollers to processors. Now, let's talk about combinational circuits, the logical brain of every digital system. These are the circuits where output depends only on the present inputs, not any past history. In simple terms, there is no memory and no feedback path, it's purely feed forward logic. Combinational circuits perform both logical and arithmetic operations using basic logic gates like AND, OR, NOT, NAND, NOR, XOR, or XNOR. Every time the input changes, the output updates instantly. There is no delay caused by the memory or clogging. Now, let's go over their key characteristics. Like their response is instantaneous, like output changes as soon as the input do. They do not store any previous value, meaning no feedback loops. They are designed using Boolean algebra and logic minimization techniques like K-maps, and they are used everywhere in arithmetic logical units, data routing, and control logic inside processors and FPGAs. Here are some of the most important building blocks of combinational circuits, which is adders used for binary addition. Like half adder adds 2 bit while a full adder adds 3 bit, including a carry. Subtractors, which performs binary subtractions. Multiplexer or mux selects one input from many. Demultiplexers or demux do not oppose it, sends one input to the multiple outputs. Encoder converts 2 to the power n input into an n-bit output, while decoder expands n-bit input into 2 to the power n outputs. Comparators compare two binary numbers and tell us whether A is greater than, equals to, or less than B. And parity generator or checker helps detect transmission error in communication systems. All these circuits are designed using truth tables and Boolean expressions and can be optimized using K-maps or logic synthesis tools. For example, a 4-bit adder subtractor circuit, an 8:1 multiplexer or 3:8 decoder, or a digital comparator inside a microcontroller, all are combinational designs. In summary, combinational circuits act as a pure logic decision maker. They do not depend on the past state, do not need a clock, and give instantaneous results. So, you can think of them as the fast, memory-less decision engine behind arithmetic units, multiplexers, and data processing blocks in every modern VLSI chip. Combinational circuits form the foundation of logic design, simple, powerful, and essential for every digital system. Now that we have covered combinational circuits, let's move on to the next major category, sequential circuits, the ones that actually remember things. Unlike combinational circuit or logic, sequential circuits depend on both the present input and the past state. They include memory elements such as flip-flop and latches, which stores the data and helps the circuit to remember what happens before. And here's the key point. Sequential circuits are time dependent. They use a clock signal to synchronize when the data gets stored, transferred, or updated. So, key characteristics of sequential circuits are: first, feedback paths are present, like the output is feedback into the circuit, allowing it to maintain states. They use storage elements to retain previous outputs. The output changes based on both input and the clock signals. They can perform complex operations like counting, storing, timing, and control, which are essential in digital systems. Let's look at the fundamental components that make sequential circuits work. First, flip-flops, the basic memory element that stores one bit of data. Common types of flip-flop which includes SR flip-flop, JK flip-flop, D flip-flop, T flip-flop, each with unique input behavior. And latches, these are the label triggered memory elements that changes state when the clock or enable signal is active. Registers, groups of flip-flop used together to store multi-bit data such as byte or words. Counters, circuits that count clock pulses either in ascending or descending order. Finite state machines like logical controls unit that transition between state based or input and clock. essential for protocol handling, controllers, and automation. Types of sequential circuits are basically there are two type of category in sequential circuits: synchronous sequential circuits and asynchronous sequential circuits. So synchronous sequential circuits are the circuit they operate in sync with the clock signal. Example includes flip-flop, registers, counters, all triggered at specific clock edge. And asynchronous sequential circuits are the circuits which depend on the input changes rather than a clock. They are faster, more complex, and prone to timing hazards. So they need careful design and verification. Sequential circuits are memory based. They retain input history and evolve over time. They are implemented using feedback loops and clocked flip-flops. They are vital for timing, control, and sequencing data in modern processors and embedded systems. Some common examples you will find in real-world design are a 4-bit shift register that moves data serially, a binary up-down counter, a traffic light controller (FSM), a UART transmitter and receiver control units, something every communication protocol uses. Sequential circuits are everywhere in microcontrollers and CPUs for program counters and control units, in communication interfaces like UART and SPI, and in timing circuits and embedded controllers that manages synchronization across a system. Sequential circuits bring memory, timing, and control into digital systems. They are the heartbeat of every processor, controller, and communication block in the modern VLSI design. Now that we have seen how logic gates and circuits work, let's understand how they are physically built. That's where the logic families come into the play. So, what exactly are logic families? They are basically groups of electronic circuits that perform logic operations like AND, OR, and NOT, but built using different underlying technologies. In simple words, they define how your gate are constructed, what devices are used, and what voltage level represents the logic 0 and logic 1. Each logic family is characterized by a few key parameters, which is speed, also propagation delay, which tells how fast a logic gate switches from one state to another. Then power consumption, which is how much energy is used during the operation. Then noise margin tells how well it can tolerate unwanted voltage fluctuations. Then fan in fan out, like how many inputs a gate can accept and how many other gates it can drive. These parameters define the performance and reliability of a digital circuit. Now let's look at some major logic families that shaped digital design history. First one is RTL, also called register transistor logic. This was the earliest logic family. It uses register and transistor to perform logic functions. Simple and low cost, but very slow and consumed a lot of power. You had find it in early computers, like before integrated circuits become common. Then TTL, transistor logic. TTL replaced registers with the transistors for faster switching. It typically operates at 5 volt, offers moderate power consumption, and has good noise margin. It became hugely popular in the 74XX series ICs, which were used in classic microcontrollers, processors, and control systems. Then ECL, emitter coupled logic. ECL took speed to the extreme. It's one of the fastest logic family ever made. It works using differential amplifier configurations which allow extremely fast switching times. But there is a trade-off, very high power consumption. ECL found its place in supercomputers and high-speed communication systems. Then CMOS, complementary metal oxide semiconductor, and finally the CMOS logic family, which dominates modern VLSI design. CMOS uses both NMOS and PMOS transistors. given its low power consumption, high speed, and excellent noise immunity. It used in microprocessors, SoCs, and memory chips. Basically, every modern digital system. Logic families define the foundation of how digital gates are physically realized. Each offers a different balance between speed, power, and reliability. But in the today's world, CMOS stands supreme as the backbone of the modern VLSI chips. Logic families define how your gates are actually built. Early designs used TTL and RTL, fast but power hungry. ECL was lightning fast but burned tons of power. And today, CMOS dominates, gives us low power, high speed, and incredible integration of VLSI chips. Now, let's talk about one of the most important part of any digital system, which is memory. Because without memory, even the most powerful chip would not know what to do next. So, what exactly is memory in digital electronics? It's the component that stores data, instructions, and intermediate results that your system needs while processing. Depending on the type, it can either hold data temporarily or permanently. In short, memory gives your chip a brain. Let's divide memory into two broad categories, volatile and non volatile memory. First one is volatile memory. This is the kind of memory that forgets everything when the power goes off. It's used for temporarily storage while the system is running, like your short term memory. Examples are RAM. This is your system's main working memory. It's fast and can read and write data quickly. Cache memory. This one even faster. It sits very close to the CPU and stores frequently accessed data so the processor doesn't have to fetch it again and again. So volatile memory is all about speed and temporarily storage. Second is non-volatile memory. Now, this type of memory remembers everything even when power is turning off. It is used for permanent or long-term storage. Examples are ROM. It stores the essential instructions needed to start your system like firmware or boot code. Flash memory. You will find this in the USB drivers, SSDs, and memory cards. It's reprogrammable and retains data even without power. EEPROM. This allows data to be erased and rewritten at the byte level, used in MCUs to store configuration or calibration data. So, non-volatile memory is like your long-term brain. It remembers what really matters. Here is something interesting. Memory is organized in a hierarchy. At the top, you have registers and cache, very fast but very small. Then comes RAM, followed by flash or ROM, and finally hard drives or external memories, larger but slower. So, the closer you are to the CPU, the faster and smaller the memory becomes. Key parameters of memories are like when designing or choosing memory, we will look at the few key factors like access time, means how quickly can you read or write data, then retention, like how long the data remains valid, then density, how much data can fit in a given area, and then power consumption, especially critical in battery powered or portable devices. All these parameters define how efficient and reliable your system's memory will be. Memory gives you chip a mind, storing not only the data it processes but also the instructions that makes it think. Memory gives your chip a mind. It's where all the data, instructions, and system states live with your circuit runs. Volatile memories are like RAM and cache. Work super fast but lose data once power is gone. Non-volatile ones, ROM, flash, EEPROM, remembers everything even after shutdown. Together, They are like the short term and long term memory of every digital system. Now, let's talk about two important data handling structures, FIFO and LIFO. Both are used to control how data is stored and retrieved in digital systems. Basically, how your system decides which piece of data to process first. FIFO, or first in, first out, works just like a queue. At the ticket counter, the first person who joins the line is the first one to be served. In digital circuits, FIFO ensures smooth or orderly data transfer, especially in communication buffers, data pipelines, or clock domain crossings. On the other hand, LIFO, or last in, first out, behaves like a stack of plate. The last plate you put on the top is the first one you take off. It's widely used in stack memory, function called storage, and even in undo redo operations in software systems. So, in short, FIFO is perfect for sequential data flow while LIFO is ideal when you need to reverse or nest operations. Together, these two concepts keep data moving efficiently and predictably across your digital design, just like organized queue, keeping everything in order. So, this brings us to the end of our session on digital electronics, the true heart of every VLSI system. We started with the basics logic gates, the fundamental decision makers of digital systems. Then we explored combinational and sequential circuits, which define how logic flows and how systems remember and react. We also looked at logic families, memories, and data handling structures like FIFO and LIFO, which brings efficiency and intelligence to the real world digital designs. Every concept we covered today, from a simple AND gate to a complex state machine, forms the foundation of what goes inside a microcontroller, a processor, or any modern chip you use today. Remember, mastering these digital basics is the first step toward becoming a confident VLSI designer. I hope you enjoyed this session, and if you did, don't forget to like, subscribe, and share my VLSI diary for more hands-on learning. In next video, we will move ahead into Verilog coding and RTL design, where all these concepts come alive in real hardware. See you there. Until the next time, keep designing, keep learning, and stay curious. Thank you.